Every theory of physics eventually runs into a wall. Sometimes the wall is experimental, a measurement that refuses to match the prediction. But sometimes the wall is mathematical, an equation that keeps working perfectly until it suddenly spits out infinity. That is what happens inside a black hole. The mathematics of general relativity, the most precisely verified theory of gravity ever written, follows a collapsing star all the way down to a single point of infinite density. And at that point, the theory destroys itself. It produces a number that has no physical meaning. Physics calls this a singularity, and for nearly a century, the smartest minds in the field have been trying to figure out whether singularities are real features of nature or signs that something in our understanding is fundamentally incomplete. The answer may have arrived from one of the most unusual corners of theoretical physics. A framework called loop quantum gravity proposes that space itself is not smooth and continuous at the smallest scales, but instead granular, made of discrete interlocking chunks. If that is true, then the collapse inside a black hole does not end in a singularity. It ends in something called a Planck star, an object so compressed it borders on the unimaginable, yet still finite, still physical, still bound by the rules of quantum mechanics, rather than crushed beneath them. The story of how physicists arrived at the Planck star is also the story of a century-long argument about whether nature permits certain kinds of catastrophe. It begins long before black holes were confirmed to exist, with a series of discoveries about what happens when matter runs out of support. The first version of the problem came from Newtonian gravity, the physics that governed science for more than 2 centuries before Einstein. In the late 18th century, the English geologist John Michel and the French mathematician Pierre-Simon Laplace both noticed something troubling. If you took enough mass and compressed it tightly enough, the escape velocity from its surface would exceed the speed of light. Nothing could get out. Michel called these hypothetical objects dark stars. His calculation showed they would need to be roughly 500 times the mass of the Sun, enormous by any measure. For a while it seemed irrelevant. A star that large would need to collapse to an implausibly small radius, and there was no known mechanism to drive that kind of compression. Then came the 20th century, and with it, a dramatically different understanding of how stars work and how they die. For most of its life, a star is a battle between 2 forces. Gravity pulls inward. The energy released by nuclear fusion pushes outward. That outward pressure, generated deep in the stellar core where hydrogen fuses into helium and eventually heavier elements, exactly balances the gravitational pull. The star maintains its size and its luminosity across millions or billions of years. But nuclear fuel is finite. When the core exhausts its supply, the outward pressure drops. Gravity wins the battle. The core collapses. For a star like the Sun, this collapse is not catastrophic in the way it might seem. As the core compresses beyond white-hot plasma into something far denser, quantum mechanics intervenes. The electrons packed into that collapsing volume begin to resist further compression in a way that has nothing to do with temperature or pressure in the ordinary sense. It is a purely quantum effect. Electrons, as fermions, obey what is called the Pauli exclusion principle. 2 electrons cannot occupy the same quantum state simultaneously. When the core reaches a density at which all available quantum states are filled, the electrons push back. This resistance is called electron degeneracy pressure, and it halts the collapse. The result is a white dwarf, a stellar remnant roughly the mass of the Sun compressed into a volume roughly the size of Earth. Dense, but stable. Nature seemed to have found a way to save the collapsing star from oblivion. Arthur Eddington, the British astronomer who had confirmed Einstein's general relativity during the solar eclipse of 1919, was convinced this kind of mechanism would always step in to prevent anything truly catastrophic. Ralph Fowler applied the emerging tools of quantum mechanics to explain white dwarfs in detail, confirming the electron degeneracy picture. It seemed like physics had a reliable safety net. Then a 19-year-old student named Subramanian Chandrasekhar stepped onto a ship bound from India to England and changed the conversation permanently. Chandrasekhar was traveling to Cambridge to study with Fowler. During the voyage, with nothing but time and his mathematical tools, he worked through a more careful calculation of the limits of white dwarf stability. He found that for white dwarfs below a certain mass, roughly 1.4 times the mass of the Sun, electron degeneracy pressure holds. But as the white dwarf gains mass and compresses further, the electrons inside it approach relativistic speeds. When you account for this correctly, the the electron degeneracy pressure no longer rises fast enough to counter the increasing gravitational squeeze. The collapse becomes runaway. There is no stable endpoint. Eddington was famously dismissive of this result. He insisted that nature must surely have some mechanism to prevent infinite collapse. He could not accept that the mathematics might be showing something real. Chandrasekhar was correct, and eventually the scientific community recognized it. But Eddington's intuition that nature intervenes before catastrophe would echo through physics for decades. For stellar masses above the Chandrasekhar limit, something else does intervene, briefly. As the collapsing core reaches densities far beyond anything in a white dwarf, the electrons are driven into the protons of the atomic nuclei. This creates neutrons through a process called electron capture. The resulting neutron-rich core, now composed almost entirely of neutrons, experiences its own version of degeneracy pressure. Neutrons, also fermions, also obey the Pauli exclusion principle. Neutron degeneracy pressure can halt the collapse at densities roughly 1,000,000 times greater than those found in white dwarfs. The result is a neutron star, an object containing 1 or 2 times the mass of the Sun compressed into a sphere only about 20 kilometers across. Neutron stars are extraordinary objects, dense enough that a teaspoon of their material would weigh more than 1,000,000,000 tons on Earth. But neutron stars have their own mass limit. Beyond roughly 2 to 3 times the mass of the Sun, the surface gravity of a neutron star becomes so extreme that even light cannot escape from its surface. An event horizon forms, a black hole is born, and this time nothing stops the collapse. The matter inside the event horizon continues to compress, and the mathematics of general relativity offers no mechanism to halt it. It predicts a singularity. For a long time, many physicists held out hope that the singularity was an artifact of the mathematics rather than a feature of physical reality. Perhaps a more realistic model of collapse, one that did not assume perfect symmetry or perfectly homogeneous matter, would avoid the singularity. That hope was definitively answered in the 1960s and 70s by a series of theorems proved by Roger Penrose and Stephen Hawking. Under very general conditions, singularities are unavoidable in general relativity. The mathematics insists on them, regardless of how the collapse proceeds. And then Hawking made things considerably worse. In 1974, Hawking combined quantum field theory with general relativity in a semi-classical calculation and found that black holes are not truly black. They emit radiation. The mechanism involves quantum vacuum fluctuations near the event horizon. Pairs of virtual particles continuously flicker in and out of existence throughout space-time. Near the event horizon, occasionally one member of such a pair falls inside while the other escapes. From a distant observer's perspective, the black hole is radiating. Energy is leaving. Over cosmological timescales, a black hole slowly loses mass and eventually evaporates entirely. This created what physicists call the black hole information paradox. Quantum mechanics has a foundational principle: information cannot be destroyed. Every physical process is in principle reversible. The quantum state of a system at any moment contains, at least in theory, complete information about its past. But if a black hole evaporates and vanishes, all the information about everything that ever fell inside it is gone. Hawking radiation is purely thermal, carrying no information about what formed the black hole. This is a direct conflict with a core principle of quantum mechanics. The information paradox remains one of the deepest unresolved problems in theoretical physics, and it is directly connected to what happens at the singularity, because whatever solution resolves the paradox almost certainly requires understanding what actually happens when matter collapses to a point. Solving the singularity problem and solving the information paradox may be two aspects of the same underlying challenge. This is where loop quantum gravity enters the picture. Loop quantum gravity, often abbreviated LQG, is one of the leading candidate theories of quantum gravity. Unlike string theory, which proposes that matter and forces are fundamentally built from one-dimensional vibrating strings in many dimensions, LQG works by quantizing spacetime itself. It proposes that space at the smallest scales is not a smooth continuum, but is built from discrete, indivisible units of area. These units interlock and combine to produce the fabric of three-dimensional space that we observe on all scales larger than what is called the Planck length. The Planck length is approximately 1.6 times 10 to the negative 35 meters. Written fully, that is approximately 1.6 times 100 septillionths of a trillionth of a meter. It is by far the smallest scale at which physics currently has any meaningful framework. Below this length, our theories of space and time simply cease to function. In loop quantum gravity, the Planck length is not just a limit of our theories. It is a genuine physical minimum. Space cannot be subdivided below this scale because there is nothing smaller. Space is, at its foundation, quantized. The elementary units of area in LQG are called spin networks, and they combine to form something called a spin foam when you include the time dimension, at scales significantly larger than the Planck length, which in practice means at essentially all observable scales. The quantized structure of LQG produces the same smooth space-time geometry described by general relativity. Any viable quantum gravity theory must do this, because general relativity is extraordinarily well verified on scales, ranging from sub-millimeter laboratory tests to the dynamics of binary pulsars to the gravitational wave signals from merging black holes. But as you approach the Planck scale, the discrete granular structure becomes relevant. And this is where LQG makes predictions that differ radically from classical general relativity. One of the most striking applications of LQG is to the early universe. Physicists working in loop quantum cosmology have applied the quantized geometry of LQG to the equations governing the expansion and contraction of the universe as a whole. These equations, called the Friedmann equations in standard cosmology, break down at the Big Bang just as general relativity breaks down inside a black hole. They predict a singularity at the very beginning of cosmic time, but when loop quantum corrections are applied, the singularity is replaced by a bounce. A collapsing universe does not crush itself to an infinitely dense point. Instead, when it reaches Planck scale density, an effective repulsive force emerges from the quantized structure of space-time. The collapse reverses. The universe bounces outward. This framework is called loop quantum cosmology, and it suggests that our universe may have preceded by a prior contracting phase, and that the Big Bang was not a beginning, but a transition. This cosmological bounce is the conceptual precursor to the Planck star. In 2014, the physicists Carlo Rovelli and Francesca Vidotto published a paper that took the loop quantum cosmology bounce and applied it to a different situation: the collapsing matter inside a black hole. The crucial insight was that while the exterior of a black hole and the cosmological setting are very different, the interior of a sufficiently massive collapsing star shares key mathematical features with a collapsing universe. Both involve matter compressing to extreme densities under its own gravity. Both produce singularities in classical general relativity, and both might therefore experience the Planck scale quantum bounce predicted by LQG. In Rovelli and Vidotto's picture, here is what happens to a star that collapses past the neutron star limit and forms a black hole. The event horizon forms. Matter inside the horizon continues to collapse. Gravity drives it toward ever greater density. In classical general relativity, this process never stops. But in LQG, as the collapsing matter approaches Planck density, the granular structure of spacetime provides an effective outward pressure. The collapse decelerates, stops, and rebounds. The singularity never forms. Instead, the matter reaches a minimum size, bounces, and begins to re-expand. For a collapsing star with the mass of the Sun, Rovelli and Vidotto estimated the size of the resulting bounced object at roughly 10 to the negative 12 meters. Written out, that is 1/1,000,000,000th of a meter, also known as 1 picometer. For context, a hydrogen atom has a radius of about 53 picometers, so a Planck star formed from a solar mass collapse would be somewhat smaller than an atom, but vastly, incomprehensibly larger than either a singularity or the Planck scale itself. This is a crucial point. The Planck star is not a singularity. It is not a point. It is not infinitely dense. It is an incredibly compressed but physically real object with a definite, finite size. It contains actual quantum states. Information is preserved within it, and it sits about 23 orders of magnitude above the Planck scale. On the scale from an atomic nucleus to the Planck length, the Planck star is much closer to the atomic nucleus. The name is somewhat misleading in this sense. The Planck star does not exist at the Planck scale. It is an object where Planck scale physics, the quantum structure of spacetime, plays a decisive role in determining its properties. It is where quantum gravity makes its stand against the singularity. Now comes one of the most counterintuitive aspects of this picture, and it requires understanding how extreme gravity affects the passage of time. Einstein's general relativity establishes that time passes at different rates in different gravitational environments. Deep inside a gravitational well, time runs slower relative to a distant observer. The stronger the gravitational field, the more pronounced this effect, which is called gravitational time dilation. Near the event horizon of a black hole, this effect becomes extreme. For an observer hovering just outside a stellar mass black hole, a clock that falls toward the horizon appears to slow down and nearly stop as it approaches the event horizon, from the hovering observer's perspective, never quite crossing it. Now imagine how extreme this effect becomes, not at the event horizon, but deep within it, at the location of the Planck star itself. The gravitational time dilation at Planck density is so severe that the Planck star's entire internal evolution, including its bounce and re-expansion outward, takes place in what for the Planck star is a very short time. But from the perspective of any outside observer, that same process is stretched across an almost incomprehensibly long duration. For a solar mass black hole, Rovelli and Vidotto's original estimate suggested the bounce timescale, as seen from outside, could be comparable to the Hawking evaporation time of the black hole, which for a solar mass object is vastly longer than the current age of the universe. This resolves what might initially seem like an obvious problem. If the Planck star bounces and explodes outward, why do we still see black holes? Why are they not immediately destroyed by the rebound? The answer is time dilation. From the outside, the internal rebound is frozen. The Planck star appears locked in its compressed state, completely invisible, completely unreachable, while the universe outside ages by astronomical timescales. The black hole persists, slowly losing mass through Hawking radiation, for what appears externally to be an enormous span of time. But from the Planck star's own reference frame, the bounce happens on a much shorter internal timescale. The situation is reminiscent of the famous twin paradox in special relativity, but far more extreme. One person ages slowly because they are moving at high speed. The Planck star ages slowly because it sits in an almost unimaginable gravitational field. The two perspectives are equally valid, equally physical. Time itself moves differently at different locations in a gravitational field. But the 2014 picture from Rovelli and Vidotto was explicitly an approximation. Several important simplifications were involved. The quantum gravitational effects were introduced as corrections to the standard equations of general relativity rather than derived fully from the underlying LQG framework, and the collapsing star was modeled as if it were a collapsing homogeneous universe, meaning the matter was treated as smooth and uniformly distributed throughout an infinite space. Real stars are neither. They are finite, bounded objects with density gradients, pressure gradients, and complex internal dynamics. Despite these approximations, the core prediction stood. Quantum gravity, applied through the lens of LQG, could provide a mechanism to halt gravitational collapse before the singularity forms. The singularity would be replaced by an ultra-dense but finite and physically real object. The information paradox would be at least partially addressed, because information would not be destroyed at a singularity that never forms. It would be preserved within the quantum states of the Planck star. In 2024, Rovelli and Vidotto published a substantially updated version of the Planck star picture that addressed what happens over the full lifetime of the system, not just the initial collapse and bounce. To understand their updated picture, it helps to recall what happens to the event horizon over time. From outside the black hole, Hawking radiation slowly carries away the black hole's energy. The event horizon gradually shrinks over a period determined by the black hole's mass. The horizon contracts until the black hole has evaporated. For a solar mass black hole, this timescale is approximately 10 to the 67th years. The current age of the universe is about 13.8 billion years, or roughly 10 to the 10th years. So the evaporation timescale is inconceivably longer than the current age of the universe. But eventually, the horizon does shrink. And as it reaches the Planck scale, loop quantum gravity predicts that the quantization of spacetime area becomes directly relevant to the horizon itself. The surface area of the event horizon cannot decrease below a minimum quantum of area. The horizon becomes stable at the Planck scale. It cannot evaporate further. This leaves behind what is called a Planck relic, a Planck-length event horizon that persists indefinitely. Planck relics are actually a fairly general prediction of quantum gravity, not unique to LQG. Many different approaches to quantum gravity suggest that the final stage of black hole Evaporation does not result in complete annihilation, but instead leaves behind a stable remnant at the Planck scale. The precise nature of these relics, and whether they have observable consequences, depends on the details of whichever quantum gravity theory is correct. But here is where the updated Planck star picture becomes particularly strange. The Planck relic event horizon has a diameter of roughly 1 Planck length. That is approximately 1.6 times 10 to the negative 35 meters. Yet within this essentially point-like horizon, recall that gravitational time dilation means space itself is enormously stretched. The interior geometry of the space-time enclosed by even a Planck-length horizon can contain far more volume than the horizon's exterior size would suggest. The Planck star inside, which for a solar mass collapse was estimated to be about 1 picometer across, is roughly 10 to the 23rd times larger than the Planck-length horizon containing it. 10 to the 23rd is 100,000 billion. That is the number of hydrogen atoms in roughly 10 grams of water. The Planck star is that many times larger than its own container, according to the exterior geometry. This is not a contradiction. It is a consequence of the extreme curvature of spacetime inside the near Planck scale horizon. In general relativity, and even more so in loop quantum gravity, the interior volume of a region is not simply determined by the area of the boundary surrounding it. When spacetime curvature is extreme, the interior can be vastly larger than a naive estimate based on the exterior would suggest. This phenomenon is sometimes called holographic encoding, or the mismatch between horizon area and interior volume, and it has deep connections to the holographic principle. The conjecture that all the information content of a three-dimensional volume can be encoded on a two-dimensional surface surrounding it. The Planck relic, with its Planck-length exterior and its comparatively enormous interior, is an extreme illustration of this geometric peculiarity. Now the picture gets stranger still. As the shrinking event horizon approaches the Planck scale during the final stages of Hawking evaporation, it experiences strong quantum effects. One of these is quantum tunneling. In ordinary quantum mechanics, particles can tunnel through energy barriers that classical physics would not permit them to cross. This happens because quantum objects do not have precisely defined positions or energies. They exist in superpositions, probability distributions spread across many possible states simultaneously. When a barrier is thin enough, or a particle's energy is close enough to the barrier height, there is a non-zero probability of finding the particle on the other side. Applied to the Planck relic and the Planck star within it, quantum tunneling means that the system can spontaneously transition from a black hole configuration to a white hole configuration. A white hole is the time reverse of a black hole. Where a black hole is a region that matter can enter but cannot exit, a white hole is a region that matter exits but cannot enter. The event horizon reverses its direction. Space and energy rush outward. In the classical picture, white holes are exotic, unstable, and probably unphysical solutions of general relativity. But in the loop quantum gravity context, the white hole emerges naturally as the time-reversed evolution of the Planck star bounce. The collapsed matter rebounds, and from the outside, this appears as a white hole. The tunneling between black hole and white hole configurations can also reverse, transitioning back from white hole to black hole. The system can cycle indefinitely, flickering between the two states in a quantum superposition. The Planck relic and the Planck star it contains exist simultaneously in both configurations, a black hole-white hole superposition maintained by the discrete quantum nature of the space-time geometry. This is deeply strange, but it is a consequence of taking quantum mechanics seriously at the extreme scales where a collapsing black hole finally confronts the granular structure of space-time. Quantum mechanics does not require objects to be in definite classical states. At the Planck scale, the distinction between black hole and white hole becomes a quantum variable, smeared across both possibilities in superposition. The implications for the information paradox are significant. In the original Hawking picture, information disappears when the black hole evaporates. In the Planck star picture, the information is preserved inside the Planck star, encoded in its quantum states. When the system eventually tunnels to the white hole configuration and the matter begins to expand outward, the information, in principle, comes back out. The information is not destroyed. It is sequestered inside the Planck relic for an enormous span of time, then eventually released. The escape of information in this scenario is extraordinarily slow by any everyday standard. The quantum tunneling probability that allows the transition to the white hole state is extremely small. The timescale over which information leaks out is comparable to the full Hawking evaporation time, which for a stellar mass black hole is far longer than the current age of the universe. For the purposes of any practical observation, the information might as well be gone. But in principle, it is preserved. The laws of quantum mechanics are respected. There is also a speculative but interesting connection to the dark matter problem. Cosmological observations across many different scales and methods consistently indicate that roughly 27% of the total energy content of the universe is in the form of matter that does not interact with light. This dark matter does not emit, absorb, or scatter electromagnetic radiation. It makes its presence known only through its gravitational effects. Its precise nature remains unknown despite decades of experimental searches. One class of proposed dark matter candidates involves compact objects rather than elementary particles. If black holes formed in the very early universe, during what is called the radiation-dominated era, before the formation of stars or galaxies, these primordial black holes could have survived to the present and contribute to the dark matter density. Searches for primordial black hole dark matter have ruled out much of the original candidate mass range, but certain windows remain open. In the Planck star framework, all black holes eventually evolve into Planck relics. If a significant population of small black holes formed in the early universe and have by now evaporated down to their Planck relic endpoints, the universe could be populated by a vast number of these extraordinarily compact objects. Each one would be essentially invisible, interacting only gravitationally, stable against further decay due to the quantization of their horizon area, and would each contain, within its stretched interior geometry, a Planck star much larger than the horizon that contains it. Whether this population of Planck relics could account for some or all of the observed dark matter depends on details that are not yet worked out. The number density required would be extraordinary. As Rovelli and Vidotto have noted, it would require a terrifyingly large number of these objects, each one a compressed shred of spacetime containing what amounts to a frozen echo of the conditions present near the beginning of the universe. It is worth pausing to appreciate how far the conceptual journey has come. The dark star of John Michel in 1783 was an object from Newtonian physics, not even a true spacetime phenomenon. Einstein's general relativity transformed it into a genuine feature of curved geometry. Chandrasekhar showed that the mass limits on stellar remnants meant black holes were physically inevitable for sufficiently massive stars. Penrose and Hawking proved that singularities were unavoidable in classical general relativity. Hawking's radiation calculation showed that black holes were thermodynamic objects, and the information paradox opened a fundamental crack in the foundations of physics. Loop quantum gravity attempts to patch that crack by replacing the continuum of space with a quantized fabric. And the Planck star is what emerges when that quantized fabric encounters the extreme compression of gravitational collapse. It is a finite physical object rather than a mathematical infinity. It carries information, it has dynamics, it bounces, and it eventually ends in a flickering quantum superposition of black hole and white hole, contained within a Planck relic smaller than any directly observable scale. What makes the Planck star picture scientifically interesting is not just that it resolves theoretical problems, though it does address both the singularity problem and, at least in principle, the information paradox. What makes it interesting is that it may be testable, at least in principle, through future observations. The transition from black hole to white hole, even if quantum tunneling makes it slow, would not be entirely silent. When the transition eventually occurs, it would produce a burst of radiation. The energy content of the burst would depend on the mass of the original black hole and the precise timescale of the tunneling. For primordial black holes that formed in the early universe with masses near or below what is called the Hawking limit, around 10 to the 15 grams, the evaporation time would be comparable to the current age of the universe. These objects might be completing their evaporation and transitioning to white holes right now, or in the cosmological near future. The radiation from such events would have characteristic properties, including specific spectral features determined by the quantum structure of the transition. Current and future gamma-ray observatories might be able to detect these bursts if enough primordial black holes of the right mass exist. The non-detection so far sets constraints on the abundance of such objects, But it does not rule out the Planck star picture. It simply constrains the parameter space. There is also the possibility of indirect evidence from the Planck relics themselves. If Planck relics accumulate over cosmic history and constitute part of the dark matter, they would have specific clustering properties and specific interactions with matter and radiation that differ from other dark matter candidates. The difference might be subtle, but future surveys of large-scale structure, combined with precision measurements of the cosmic microwave background, could in principle distinguish between a smooth, particle-like dark matter component and one that includes a population of compact Planck relics. For the moment, these observational tests remain speculative. The Planck scale is so far beyond the reach of any current experiment or observation that direct confirmation of LQG is not available. The theory has not yet made a prediction that has been confirmed in a way that distinguishes it from competing theories. This is a genuine challenge for loop quantum gravity and for quantum gravity research generally. The energy scales at which quantum gravity effects become important are roughly 10 to the 28 electron volts, more than 15 orders of magnitude above what the Large Hadron Collider can probe. The gap between the theoretical frontier and the experimental frontier is enormous. Bridging it requires either finding indirect observational signatures, like the Planck relic dark matter signal, or developing new conceptual tools that connect Planck-scale physics to measurable phenomena at accessible energies. Some researchers have proposed that the cumulative effect of Planck-scale discreteness on photons traveling over cosmological distances might produce a measurable dispersion effect, with different frequencies of light arriving at slightly different times from distant sources. Observations of gamma-ray bursts with the Fermi Gamma-Ray Space Telescope have placed tight constraints on this possibility, ruling out some of the simpler LQG-inspired models. The relationship between loop quantum gravity and string theory, the other major approach to quantum gravity, remains somewhat adversarial. String theory has its own proposed resolution of the singularity problem in the form of objects called fuzzballs. In the fuzzball picture, a black hole is not a region of empty curved spacetime with a singularity at the center. Instead, all of the string-theoretic matter that formed the black hole unravels into its underlying stringy constituents, which fill the entire volume beneath the horizon. The fuzzball has no singularity and no sharp horizon in the classical sense. It is a quantum mechanical object in which matter and geometry are entangled across the entire interior. The fuzzball picture resolves the information paradox because information is encoded in the string configurations throughout the fuzzball and is gradually released in the Hawking radiation through a scrambling mechanism. The Planck star and the fuzzball represent two different answers to the same question. What replaces the singularity? They come from very different theoretical frameworks and make different predictions about the properties of black hole interiors, the nature of Hawking radiation, and the endpoint of black hole evaporation. In the absence of experimental data that distinguishes between them, both remain viable possibilities. The scientific question is open. There is a deeper sense in which both approaches represent a fundamental shift in how physicists think about the interior of black holes. For most of the 20th century, the question of what happens inside a black hole was considered, in a practical sense, irrelevant. Information that fell inside could not, in classical general relativity, influence anything outside. The interior was causally disconnected from the observable universe. Whatever happened there was, in principle, beyond the reach of any experiment. The discovery of Hawking radiation changed this. If black holes evaporate, then eventually the information encoded in their interiors must return to the outside universe, or be lost forever. The interior is not causally irrelevant after all. Whatever happens at the singularity, or wherever it is replaced, has consequences for the observable universe through the final stages of evaporation. The physics of the interior matters, even for an observer who never crosses the horizon. This is why so much theoretical effort is focused on the interior structure of black holes. The singularity is not just an aesthetic problem. It is a diagnostic. The way you resolve the singularity determines how you resolve the information paradox, and the resolution of the information paradox may reveal something fundamental about the relationship between quantum mechanics and gravity, the two pillars of modern physics that have resisted unification for a century. The Planck star is, in this context, one of the most concrete proposals for what that resolution might look like. It is not vague. It makes specific predictions about the structure of the collapsed object, the timescale of the bounce, the nature of the endpoint, and the possible observational signatures. It is grounded in a specific theoretical framework, loop quantum gravity, which itself makes definite predictions about the quantization of spacetime at the Planck scale. It can be falsified, in principle, by sufficiently sensitive observations of gamma-ray bursts, dark matter structure, or the final stages of black hole evaporation. The fact that we cannot yet test it does not make it unscientific. It makes it a prediction waiting for the instruments and techniques that can catch up to it. One of the more philosophically interesting aspects of the Planck star picture is what it implies about time and causality at extreme scales. The notion that an object can persist frozen in an enormous gravitational time dilation for vastly longer than the current age of the universe, while internally experiencing a bounce that plays out on a far shorter timescale, challenges ordinary intuitions about the relationship between internal and external time. A Planck star formed from the collapse of a massive star billions of years ago might, from its own internal perspective, have already bounced. But from the perspective of any external observer, the black hole it formed is still there, still shrinking glacially through Hawking radiation, with the internal rebound inaccessible and invisible until the very end stages of evaporation. This is not paradoxical in the technical sense. Both descriptions are consistent with the laws of physics. Gravitational time dilation is well understood and experimentally confirmed at far less extreme scales. GPS satellites need relativistic corrections to remain accurate. Atomic clocks at different altitudes run at measurably different rates. The physics is real. The Planck star picture simply extends it to the most extreme version imaginable. What makes it conceptually unsettling is the disconnect between internal and external time at this extreme. In everyday experience, objects have one time. They age at one rate. The clocks inside and outside a building differ by billionths of a second over a year, a difference that requires precision atomic clocks to detect. Near a Planck star, the same physics that produces billionths of a second of difference per year produces a difference of many orders of magnitude over the age of the universe. The same equations, extended to conditions we have never directly observed. Loop quantum gravity remains incomplete. The full theory has not been solved. The connection between the Planck scale and the macroscopic scale of general relativity is not fully worked out. The predictions of LQG for cosmological observables are still being developed. The Planck star itself is, as Rovelli and Vidotto have emphasized, based on approximations that will need to be refined as the theory develops further. The 2024 update represents progress, but not a complete solution. What has been established is that a mechanism exists, at least within the LQG framework, to replace the singularity with something finite. The mathematics does not necessarily produce infinity at the center of a black hole. It can, under the right conditions and with the right theoretical input, produce something small but real, something that carries information, that has dynamics, that bounces, and that persists in some form until the very end of the black hole's long life. From the perspective of the history of physics, this continues a pattern that has repeated itself many times. A theory works brilliantly until it predicts an infinity or an impossibility. Nature is examined more carefully. A new mechanism is found that prevents the catastrophe. The theory is extended, refined, or replaced. Dark stars gave way to stars with event horizons. Event horizons with singularities gave way, perhaps, to event horizons with Planck stars. The progression is not toward fewer mysteries, but toward more precisely located ones. The singularity at the center of a black hole was a mystery that pointed to the incompleteness of classical gravity. The Planck star is a proposed answer that points to the next layer of mystery, the quantum structure of space-time itself. Whether that structure is correctly described by loop quantum gravity, or by string theory, or by some framework not yet developed, is the question at the frontier. What is clear is that the interior of a black hole is not a dead end. It is not a place where physics goes to die. It may be, if the Planck star picture is correct, a place where space-time itself undergoes a fundamental quantum transformation, where the structure of gravity at the smallest possible scale confronts the density of the collapsed matter and wins, just barely, preventing the ultimate catastrophe of infinite compression. A tiny ball of matter, smaller than an atom, containing within itself conditions similar to those present in the early moments of the universe, frozen by time dilation inside a relic event horizon smaller than any directly observable length. Carrying information about everything that ever fell inside its parent black hole, waiting across timescales that dwarf the current age of the cosmos, for the slow quantum tunneling event that will allow it to emerge. That is what the Planck star might be. Not a singularity, not a point, a frozen echo of the Big Bang, preserved inside the most extreme object in the known universe, kept alive by the quantum granularity of space itself. Whether it is real is a question that future physics will have to answer. But the fact that such an object is theoretically possible, that the mathematics of loop quantum gravity permits it, that it resolves genuine problems that classical general relativity cannot, that it makes at least some predictions that are in principle testable, means it deserves to be taken seriously. The universe may be more forgiving than Einstein's equations suggest, or more precisely, the universe may operate on rules that Einstein's equations approximate beautifully at large scales, but cannot fully describe at the smallest ones. That gap between the approximation and the reality is where the Planck star lives. Where the singularity was, there may instead be something far stranger, and in a strange way far more interesting. An object that sits at the absolute boundary of what we can describe with current physics, pointing toward everything we have yet to understand. If you found this exploration of black hole interiors, loop quantum gravity, and the Planck star valuable, consider subscribing for more rigorous examinations of the frontiers of physics and cosmology. There is more to cover, and the questions only get deeper. The history of physics is, in a meaningful sense, a history of singularities, not just in the mathematical sense of points where equations break down, but in the broader sense of moments where a framework that had worked perfectly reveals its own edges. The singularity inside a black hole is one of those edges. It is where the most successful theory of gravity ever developed, tested to extraordinary precision across an enormous range of scales and phenomena, finally says, "I cannot tell you what happens here. This is not a failure of general relativity in the ordinary sense. The theory is not wrong. It is incomplete. There is a regime, specifically the regime of Planck scale densities and energies, where additional physics must enter. Every physicist working on quantum gravity knows this. The disagreement is about what that additional physics looks like. To understand why loop quantum gravity takes the specific form it does, and why it leads to the Planck star in particular, it helps to appreciate the core conceptual challenge involved in quantizing gravity. Quantum mechanics and general relativity were developed independently in the early 20th century, and they were developed to describe different domains. Quantum mechanics was built to describe the behavior of atoms, subatomic particles, and radiation. It is a theory of discreteness, probabilities, and wave functions. Its domain is the very small. General relativity was built to describe the behavior of gravity, the large-scale structure of spacetime, and the motion of massive bodies from planets to galaxy clusters. It is a theory of smooth, continuous geometry. Its domain is the very large. In everyday physics, both theories are applied without conflict, because the phenomena in each domain do not significantly overlap. Gravity is so weak at atomic scales that quantum effects in gravity are completely negligible, and the quantum discreteness of atomic physics is completely negligible at the scale of planets and stars. But in extreme environments, both sets of effects become simultaneously important. In the very early universe, when all the matter and energy that now comprises the observable cosmos was compressed into a volume smaller than a proton, quantum effects and gravitational effects were equally dominant. At the singularity inside a black hole, the same is true. You cannot understand what happens in these regimes without a theory that seamlessly incorporates both quantum mechanics and general relativity. The challenge is that the two theories are, in a technical sense, incompatible. They use different mathematical languages, rest on different fundamental assumptions about the nature of space and time, and produce results that conflict when you try to apply both simultaneously. General relativity describes a smooth, dynamical spacetime. Quantum mechanics is formulated on a fixed, flat background spacetime. In general relativity, the gravitational field is the geometry of spacetime itself. In quantum mechanics, fields are quantized by promoting them to operator-valued distributions on a fixed background. Trying to apply this quantization procedure to the gravitational field, which is the spacetime background itself, leads to a deeply circular problem. The field you are trying to quantize is the stage on which the quantization process is supposed to take place. String theory handles this problem by assuming additional dimensions and additional fundamental constituents, the strings. and showing that gravity emerges as a low-energy effective theory from their interactions. The framework is rich enough to define quantization in a meaningful way because the strings live in a higher dimensional spacetime that provides the necessary background structure. Loop quantum gravity takes a different approach. Rather than assuming a background spacetime and quantizing fields on it, LQG tries to quantize spacetime geometry directly. It takes the key insight of general relativity, that gravity is geometry, seriously at the quantum level. In LQG, the basic variables of the theory are not the metric tensor of general relativity, which describes distances and angles at every point of spacetime, but instead more abstract geometrical quantities called Ashtekar variables, related to the curvature and connection of the spacetime manifold. When you quantize these variables, you find that the resulting quantum states of spacetime are not smooth continuous geometries. They are discrete networks, the spin networks mentioned earlier, in which area and volume come in discrete chunks. The smallest chunk of area is on the order of the Planck area, which is the Planck length squared, roughly 10 to the negative 70 square meters. The smallest chunk of volume is the Planck volume, the Planck length cubed, roughly 10 to the negative 105 cubic meters. These are so fantastically small that no conceivable experiment conducted at accessible energies could directly detect them. But their existence changes the physics at extreme densities. When matter is compressed to Planck density, the discrete structure of spacetime becomes the dominant physics. The smooth geometry approximation of general relativity breaks down completely. The granular quantized nature of space asserts itself, and in the LQG description of this regime, the granularity provides an effective repulsive effect that resists further compression. This is not a force in the ordinary sense. It is a consequence of the quantization of geometry. You cannot compress spacetime below the minimum unit of area. When you try to push more matter into a smaller volume, you run out of spacetime to put it in. The bounce is the result. This is conceptually analogous to, but physically distinct from, the electron degeneracy pressure that supports white dwarfs. In the white dwarf case, the Pauli exclusion principle prevents electrons from occupying the same quantum state. In the Planck star case, the quantization of spacetime prevents geometry from collapsing below the minimum scale. Both are quantum effects that provide an effective resistance to further compression, but they operate through completely different physical mechanisms and at wildly different scales. The Pauli exclusion principle that supports white dwarfs becomes relevant at densities around 100 million tons per cubic centimeter. The LQG quantum geometry effects that produce the Planck star bounce become relevant at Planck density, which is approximately 5.1 times 10 to the 96th kilograms per cubic meter, or roughly 500 million billion times denser than water. The gulf between these two density scales is as enormous as the gulf between everyday physics and quantum gravity. One of the important developments in the Planck star story is the realization that the white hole that forms after the bounce is not a separate, independent object from the black hole. They are two aspects of the same quantum gravitational process. In the classical general relativity picture, black holes and white holes are distinct solutions of Einstein's equations, related by time reversal, but otherwise separate. In the loop quantum gravity picture, the collapsing matter that forms the Planck star can tunnel between the black hole and white hole configurations. The two are connected by a quantum amplitude. The system is in a superposition of both. This quantum superposition of black hole and white hole has implications for how information escapes. In the standard Hawking picture, Hawking radiation is thermal and carries no information. The information about what formed the black hole is encoded in the interior quantum state. In the Planck star picture, the information encoded in the Planck star is slowly correlated with the outgoing Hawking radiation through the quantum tunneling process. The information leaks out over the Hawking evaporation timescale, not all at once in some catastrophic final burst. The outgoing radiation is not purely thermal. It contains, hidden in subtle quantum correlations, the information about everything that ever fell inside. This is similar in spirit to what has been called black hole unitarity, the proposal that black hole evaporation is a unitary quantum process that preserves information. The precise mechanism by which unitarity is maintained has been debated intensely since Hawking's original calculation. The Planck star mechanism is one concrete proposal for how the unitarity might be achieved. The Hawking information paradox has generated more theoretical papers than almost any other problem in modern physics. A partial resolution called the Page curve, after the physicist Don Page, who first described it, says that if black hole evaporation is unitary, then the entanglement entropy of the Hawking radiation should initially increase as the black hole evaporates and then decrease back to zero as the black hole approaches its endpoint, forming a characteristic curve. Recent calculations using ideas from holography and replica wormholes have provided evidence that the Page curve is indeed reproduced in some versions of string theory, suggesting that information is preserved. But the precise mechanism in loop quantum gravity, and specifically in the Planck star framework, is still being worked out. The intersection of the Planck star picture with the holographic principle is particularly interesting. The holographic principle, motivated by the thermodynamics of black holes and developed into a precise conjecture by Juan Maldacena in 1997 in what is called the ADS-CFT correspondence, proposes that the information content of a three-dimensional volume can be completely encoded on a two-dimensional boundary surrounding it. Applied to black holes, this means all the information about the interior should be encoded on the event horizon. In the Planck relic, which has an event horizon of Planck area, the maximum information content according to the holographic bound is roughly 1 bit. Yet the interior Planck star, which is vastly larger than the Planck scale, should encode an enormous amount of information about the collapsed star. This apparent conflict is one of the open problems in the Planck star picture. How can a Planck relic with a 1-bit holographic capacity contain a Planck star encoding the quantum state of an entire stellar collapse? Different researchers in the LQG community have proposed different resolutions. Some argue that the holographic principle does not apply straightforwardly at the Planck scale, where spacetime discreteness changes the rules. Others propose that the information is gradually transferred to the outgoing Hawking radiation during the long evaporation phase, leaving only a tiny residual in the Planck relic. The question is not resolved. Another open issue is the stability of the Planck relic itself. If quantum tunneling allows the relic to transition between black hole and white hole configurations, and if this transition can release energy, then the relic is not truly stable in the absolute sense. It will eventually discharge its information and energy content. The timescale for this is determined by the tunneling amplitude, which is expected to be extremely small. But what exactly the endpoint of this process looks like, whether the relic completely evaporates or leaves behind some more fundamental residue of space-time structure, is not yet clearly determined within the LQG framework. These unresolved questions are not signs of failure. They are the normal status of a research program that is actively developing. The Planck star picture in 2024 is more complete and more detailed than it was in 2014. The 2014 picture itself was more complete than the initial proposals about quantum gravity and black hole interiors that preceded it. The direction of progress is clear, even if the destination is not yet in sight. It is also worth noting that the Planck star picture, if correct, has implications beyond black hole physics. It suggests that the Big Bang singularity, the beginning of our universe in the standard cosmological model, is similarly replaceable. In loop quantum cosmology, the universe did not begin in a singularity. It bounced from a prior contracting phase. The Big Bang was a big bounce. The conditions at maximum compression in that bouncing cosmology are analogous to the conditions in the Planck star. In both cases, Planck density is reached. In both cases, LQG predicts a quantum bounce rather than a singularity. In both cases, the singularity is replaced by something finite and physical. This parallel between the cosmological and stellar contexts is not a coincidence. It reflects a deep property of loop quantum gravity, that the quantum corrections to classical general relativity that prevent singularities in one context also prevent them in the other. The same physics that gave Rovelli and Vidotto their first picture of the Planck star came from the cosmological application of LQG. The two problems, the singularity inside a black hole and the singularity at the Big Bang, may have a common solution in the quantized geometry of loop quantum gravity. This has a striking philosophical implication. If the Big Bang was a bounce rather than a beginning, then the universe has a history that extends before the current expansion. What that prior history looked like, how far back it extends, whether it is knowable in principle from observations of the current universe, These are questions that loop quantum cosmology is beginning to address. Some signals from the pre-bounce phase might survive in the form of subtle anomalies in the cosmic microwave background, the relic radiation from the hot early universe, current and future observations of the CMB with instruments like the Simons Observatory, and CMB S4 might reveal or rule out these signatures. The connection between the Planck star and the Big Bounce is a reminder that physics at the largest and smallest scales is not separate. The universe as a whole and a collapsing stellar core, both in extreme conditions, confront the same Planck scale physics. The tools developed to understand one illuminate the other. The scientific journey from Michel's dark stars to the Planck star spans 2.5 centuries, 3 major revolutions in physics, the deepest theoretical crisis in modern fundamental physics, and an ongoing research program that reaches to the absolute limits of what any current theory can describe. Along the way, every proposed mechanism to avoid the black hole was eventually overturned by new physics. Dark stars were too large to form. Quantum degeneracy pressure halted stellar cores, but only up to a mass limit. Above that limit, the event horizon was unavoidable. But inside the event horizon, the story may not be finished. Loop quantum gravity proposes that the collapse terminates not in a singularity, but in a Planck star. A bouncing, information-preserving, quantum mechanically consistent object at the limits of what spacetime itself can support. The theoretical evidence for this possibility is real, even if the experimental confirmation is far away. The mathematical framework exists. The predictions, at least in principle, are testable. The picture, while incomplete, is coherent. Physicists have been fighting this battle against the singularity for a century. The Planck star suggests the battle may not be lost. Nature may indeed step in to prevent the ultimate collapse, just as Eddington always hoped, though by mechanisms far stranger than anything Eddington could have imagined. The question of what exists inside a black hole is not purely academic. It is connected, through the threads of quantum information theory, to fundamental questions about the nature of physical reality. Quantum mechanics tells us that information is never truly destroyed. This principle is encoded in the unitarity of quantum evolution, the requirement that the time evolution of a quantum system preserves probability and is, in principle, reversible. You can evolve any quantum state forward in time, and you can also run the evolution backward. Nothing is truly lost. But classical gravity, by creating an event horizon from which nothing can escape, appears to violate this principle. Information falls in, the black hole evaporates, the information is gone. This violation is not subtle or debatable within classical general relativity. Combined with semi-classical quantum field theory, it is explicit. Hawking's calculation is unambiguous on this point. The thermal radiation contains no information about what formed the black hole. If you watched a black hole evaporate completely, you would be left with featureless thermal radiation that could have come from any black hole of that original mass, regardless of what fell in. To many physicists, this is simply unacceptable. Not on aesthetic grounds, but because the unitarity of quantum mechanics is one of the most deeply tested and verified principles in all of physics. It underlies the extraordinary precision of quantum electrodynamics, the standard model of particle physics, the entire framework of quantum chemistry. To abandon it would require abandoning nearly all of modern physics along with it. The information paradox is therefore a genuine crisis, not a curiosity. It means that quantum mechanics and general relativity, as they currently stand, cannot both be correct. The resolution must come from quantum gravity, the theory that replaces both in the extreme regime. And different quantum gravity theories offer different resolutions. In the string theory context, the most developed resolution involves the idea that the black hole horizon is not an empty region of space, as classical general relativity suggests, but is instead the location of a complex quantum system, sometimes described as a stretched horizon, or as the boundary of the fuzzball. The information is encoded in the quantum state of this system, and is gradually imprinted on the Hawking radiation through a scrambling process. In the loop quantum gravity context, the Planck star provides the storage location for the information. The quantum states of the Planck star encode everything that ever fell in. The information is not immediately released, but it is preserved. Over the enormous evaporation timescale, the quantum tunneling between black hole and white hole configurations allows the information to slowly leak back into the exterior universe. The process is unitary. The information is never destroyed. Both of these pictures are incomplete. Both make assumptions and approximations. Both face technical challenges that have not been fully resolved. But both represent serious attempts to take the information paradox seriously and to identify a physically coherent mechanism for resolving it within specific theoretical frameworks. The Planck star is, in this sense, not just a curiosity about black hole interiors. It is a proposal about the foundations of physics. It is a claim that the information principle of quantum mechanics is not violated, that the laws of nature are consistent, that the apparent paradox between gravity and quantum mechanics is resolved at the Planck scale in a specific, definite way. Testing this claim experimentally is the challenge of decades or centuries to come. The energies involved are inaccessible. The timescales are incomprehensible by human standards. The objects involved are smaller than any directly detectable scale, but the theoretical work can still make progress. The predictions can be made sharper. The internal consistency of the framework can be checked more thoroughly. The connection to potential observational signatures, however indirect, can be developed more carefully. The Planck star picture has already evolved significantly between 2014 and 2024. It will continue to evolve as loop quantum gravity matures, as its predictions for other phenomena are worked out and tested, as the connection between Planck-scale physics and accessible observations is developed. Whether the Planck star survives this evolution or is replaced by something more complete remains to be seen. What is certain is that the question it addresses, what happens at the center of a black hole, will not go away. It is one of the defining questions of fundamental physics. It sits at the intersection of every major unsolved problem in the field: quantum gravity, the information paradox, the nature of spacetime at the smallest scales, the origin of dark matter, the prehistory of the universe. Any theory that hopes to be the final word on the physics of nature must give a coherent answer to this question. The Planck star is one proposed answer. Clear, specific, grounded in a concrete theoretical framework, connected to physical mechanisms that resolve genuine problems, and at least in principle, testable through future observations. It deserves the attention of anyone who takes seriously the question of what physics, at its most extreme, actually looks like. There is something fitting about the idea that the most extreme object in the universe, the black hole, conceals at its heart something that resembles the beginning of everything. The conditions in the Planck star, Planck density, Planck temperature, quantum space-time geometry asserting its dominance over smooth classical space, are the same conditions that loop quantum cosmology says characterized the Big Bounce that gave rise to our expanding universe. The black hole and the universe, at their most fundamental level, share the same physics. The collapse that formed one, and the expansion that produced the other, may be mirror images of the same quantum gravitational process. A black hole, in this picture, is not a dead end. It is a transformation. Matter falls in, collapses, reaches the limit of what space-time can sustain, bounces, and eventually, after vast timescales, emerges again. Not as the same matter, perhaps, but as radiation carrying information about what once was. But the picture is not arbitrary. It follows from specific, theoretical inputs that are themselves motivated by the genuine requirements of a consistent quantum theory of gravity. Physics has often advanced by taking seriously the logical implications of theories, even when those implications seemed strange. The existence of atoms was dismissed as a mere mathematical convenience before it was confirmed experimentally. The expansion of the universe was initially rejected by its own discoverer as a mistake. Black holes themselves were considered by many leading physicists to be unphysical artifacts of excessive mathematical idealization right up until the evidence became overwhelming. The Planck star may be in the same position today, a theoretical construct that seems too strange, too extreme, too far from anything observable to be taken seriously. Or it may be what really happens inside a black hole. The mathematics says it is possible. The physics says it would resolve genuine problems. The theory that predicts it makes correct predictions in other domains, and the observations needed to test it may be achievable in the future, even if not today. In the meantime, the black holes continue. They merge and emit gravitational waves that cross billions of light years to be measured in instruments sensitive enough to detect a displacement smaller than 1,000th the diameter of a proton. They power quasars that outshine entire galaxies. They sit at the centers of galaxies like our own, with masses millions or billions of times the mass of the Sun, surrounded by spiraling accretion disks of superheated matter. They were imaged for the first time in 2019. First, the supermassive black hole at the center of the galaxy Messier 87, then the black hole at the center of our own Milky Way, Sagittarius A star. Inside each of these objects, if loop quantum gravity is right, sits a Planck star, a ball of quantum spacetime smaller than an atom, larger than a singularity, carrying within it the information about everything that ever fell inside, frozen by time dilation so extreme that from the outside it appears to have not moved at all since the moment the black hole formed, waiting across spans of time that make the current age of the universe look brief, for the quantum tunneling event that will eventually allow it to begin its rebound. The universe is patient in ways that make any human timescale seem instantaneous, and at the heart of every black hole, time may be operating by rules so different from anything we directly experience that the concepts of before and after, inside and outside, past and future, require completely new frameworks to describe. The Planck star lives in that territory, at the boundary of what our current theories can say, pointing toward what they cannot. The scientists who work on this problem are not just solving an abstract puzzle. They are trying to understand what physical reality looks like at its most fundamental level. The answer, when it comes, will be one of the deepest discoveries in the history of science. Whether it takes the form of a Planck star or something else entirely, it will reveal the rules that govern the universe at scales and densities where no observation has yet reached. And in doing so, it will complete the picture of gravity that Einstein began more than a century ago. To fully appreciate the significance of the Planck star, it is worth examining more carefully what we actually know about black holes from observation, and what remains genuinely unknown. The gap between what we can observe and what the theory predicts is where the most important physics lives. The first indirect evidence for black holes came from X-ray astronomy in the early 1970s. When gas falls toward a compact massive object, it forms a spiraling accretion disk. Friction within the disk heats the gas to temperatures of millions of degrees, causing it to emit X-rays. Cygnus X1, a bright X-ray source in the constellation Cygnus, was identified in 1972 as a binary system consisting of a blue supergiant star and an unseen compact companion. The companion's mass, inferred from the orbital dynamics of the binary, exceeded the maximum mass for a neutron star. The invisible, X-ray bright compact object was a black hole. Since then, thousands of black hole candidates have been identified through their effects on surrounding matter, companion stars, and in the case of galactic-scale jets, on the structure of entire galaxies. The detection of gravitational waves by LIGO and Virgo beginning in September 2015 added a completely independent line of evidence. The first detection, GW 1500914, was the signal of two black holes merging. Their masses were roughly 36 and 29 times the mass of the Sun. The merger produced a final black hole of about 62 solar masses, releasing the remaining 3 solar masses as gravitational wave energy. The waveform matched the predictions of general relativity with extraordinary precision. Gravitational wave astronomy has since detected dozens of black hole mergers, covering a range of masses from a few solar masses up to several tens of solar masses for the individual progenitors, and revealing that black holes with masses in the range of roughly 25 to 65 solar masses are more common than previously expected. This has opened new questions about the formation pathways of black holes in this mass range, since certain mechanisms of stellar evolution have difficulty producing black holes. At the upper end of this range, the Event Horizon Telescope collaboration released its first image of a black hole in April 2019. The target was the supermassive black hole at the center of the galaxy Messier 87, designated M87 star. Its mass is approximately 6.5 billion times the mass of the Sun, and it sits about 55 million light-years from Earth. The image showed a bright ring of emission surrounding a dark central region, the shadow of the event horizon. The size and shape of the shadow matched the predictions of general relativity to within the measurement uncertainty. In 2022, the Event Horizon Telescope released the first image of Sagittarius A star, the 4 million solar mass black hole at the center of our own galaxy, about 26,000 light-years away. These images are extraordinary achievements. They represent the first direct visual evidence for the event horizon, the causal boundary that separates the interior of the black hole from the observable universe. The bright ring surrounding the shadow is light that has been bent by the extreme gravity of the black hole, orbiting multiple times before escaping to reach the telescope. The dark region in the center is genuinely dark, not because it emits no light, but because any light emitted inside the horizon cannot reach us. What the event horizon telescope cannot see is what happens inside that dark region. The horizon is, by definition, a one-way boundary. Light and matter can cross it inward, but nothing comes back. All of our information about black hole interiors is necessarily theoretical. We infer the interior structure from the external behavior of the black hole and from the mathematical predictions of whatever theory we trust. This is a fundamental epistemological limitation of black hole physics. The interior is causally disconnected from us. We can study the event horizon, the accretion disk, the jets, the gravitational wave signals from mergers, but we cannot directly probe what happens inside. This makes the singularity problem all the more vexing. Not only do we not know what replaces the singularity, we cannot directly observe the interior to check. Whatever resolution we find must be theoretically motivated and tested through indirect means. The indirect tests that are potentially available are primarily through the final stages of black hole evaporation. As a black hole loses mass through Hawking radiation, it becomes smaller, hotter, and eventually, if it reaches the Planck scale, qualitatively different. A Planck scale black hole is in the fully quantum gravity regime. Its behavior cannot be described by semi-classical methods. The predictions of any quantum gravity theory for a Planck scale black hole, whether it is loop quantum gravity or string theory or something else, are therefore most testable in the late stages of evaporation. For stellar mass black holes, the evaporation time is so enormous that observing the late stages is completely impractical. But primordial black holes, if they exist, with masses below about 10 to the 15 grams, would have evaporation times comparable to the current age of the universe. Some of these, with masses at exactly the right value, might be completing their evaporation right now, in this cosmological epoch. The radiation from this final evaporation, and especially from any Planck star rebound or Planck relic transition, would be detectable in principle by gamma-ray instruments if it occurs frequently enough. The Fermi Gamma Ray Space Telescope, launched in 2008, has been the primary instrument searching for signatures of primordial black hole evaporation. So far, no such signal has been detected. The absence of detection constrains the abundance of primordial black holes with masses near 10 to the 15 grams. But the constraints depend on assumptions about the spectrum and character of the radiation produced in the final stages of evaporation. And these assumptions change, depending on what the correct quantum gravity theory predicts. Different theories, including the Planck star picture, predict different final evaporation signatures, working out the precise observational prediction of the Planck star model for the gamma ray. Signature of a primordial black hole completing its evaporation is one of the active areas of research in this field. The prediction requires understanding not just the thermodynamics of Hawking radiation, but also the quantum tunneling transition to the white hole configuration, the spectrum of radiation produced in that transition, and how this radiation propagates through the universe to reach a detector. Each of these steps involves approximations and assumptions that are currently being refined. Another observational window comes from the density and distribution of dark matter. As mentioned earlier, Planck relics might contribute to or entirely constitute the dark matter. The clustering properties of dark matter derive from the distribution of galaxies, galaxy clusters, and the cosmic microwave background are consistent with what is called cold dark matter, a component that was already non-relativistic when it first became gravitationally relevant in the early universe. Planck relics, being extremely compact and massive, would qualify as cold dark matter. Their gravitational effects would be indistinguishable from other cold dark matter candidates at the scales probed by large-scale structure observations. However, some observational tests are sensitive to the internal structure of dark matter particles in ways that could distinguish between elementary particles and compact objects. Microlensing surveys, which look for the transient brightening of background stars when a dark object passes in front of them, have constrained the fraction of dark matter that could be in compact objects of various masses. For masses around the mass of the Moon to around 10 times the mass of the Sun, These constraints are tight. For smaller masses, including the mass range of Planck relics, the constraints are weaker and the window remains open. Future surveys, including the Rubin Observatory Legacy Survey of Space and Time, will push the microlensing constraints to smaller masses and greater distances, potentially probing the mass range most relevant for Planck relic dark matter. Combined with observations of the gravitational wave background from compact binary mergers, these surveys might eventually determine whether a significant population of Planck mass compact objects exists in the dark matter halo of our galaxy. None of this will be a definitive test of loop quantum gravity in the near term. The theoretical uncertainties are too large, and the observational uncertainties are too significant. But the constraints will narrow over time. Each non-detection in a specific mass range rules out models that predict abundant Planck relics in that range. Each positive detection, if it occurs, would open an entirely new field of observational quantum gravity. The theoretical development of loop quantum gravity itself is proceeding on multiple fronts. The mathematics of spin networks and spin foams has been developed extensively since the 1990s. The dynamics of LQG, specifically the question of how spin network states evolve in time, is governed by what is called the Hamiltonian constraint, or, in the covariant spin foam approach, the amplitude for transitions between different quantum spacetime geometries. Working out the precise predictions of these dynamics for physically relevant situations, such as the collapse of a star to a black hole, requires sophisticated calculations that are still in progress. One of the major technical challenges is bridging the gap between the fundamental Planck scale description of LQG and the macroscopic description of general relativity. This is called the semi-classical limit problem. Any quantum gravity theory must reduce to general relativity in the appropriate limit. For loop quantum gravity, demonstrating this reduction rigorously, showing that the dynamics of spin foams leads to Einstein's equations on scales much larger than the Planck scale, has been technically difficult. Progress has been made, particularly in simplified models, but the full general case is not yet established. This is not a fatal problem for the theory. Most theories in physics require careful work to establish their semi-classical or classical limits. Quantum mechanics reduces to classical mechanics in the limit of large quantum numbers. Quantum field theory reproduces classical electrodynamics in the appropriate limit. The challenge in LQG is that the calculation is more technically demanding because the structure of the theory is more unusual. But the consistency checks that have been done are encouraging. Loop quantum cosmology, which is the application of LQG to the homogeneous isotropic universe, does reproduce the Friedmann equations of standard cosmology on large scales, with corrections that become significant only near the Planck scale. The calculation that led to the Planck star was done in a simplified model that applied the loop quantum cosmology, corrections to the interior of a collapsing star. This model captures the essential physics of the bounce, but lacks the detail needed to compute precise predictions for observational signatures. More complete calculations using the full spin foam dynamics applied to a realistic collapsing star are needed. This is a technically challenging project that will occupy researchers for years to come. The parallel development of numerical methods for loop quantum gravity is, therefore, an important part of the research program. Just as numerical relativity was essential for making precise predictions of gravitational wave signals from black hole mergers, numerical loop quantum gravity will be essential for making precise predictions of the Planck star bounce and its observational consequences. The field is at an early stage in this direction, but the tools are being developed. In this context, it is worth appreciating the remarkable success of numerical relativity in the context of gravitational wave astronomy. The first LIGO detection in 2015 relied on theoretical waveform templates computed by numerical relativists over the preceding decades. Computing the gravitational waveform from two merging black holes required solving Einstein's equations numerically on a computer, a task that was beyond the reach of any computer until the early 2000s. The breakthroughs that made this possible, particularly the moving puncture method developed independently by groups in 2005, enabled the computation of stable, accurate waveforms for the full merger and ring-down process. The same level of computational effort applied to the interior dynamics of a black hole in the framework of loop quantum gravity could, in principle, yield precise predictions for the Planck star bounce and the associated radiation. The calculations would be far more challenging because they require the full quantum gravity description rather than the classical general relativity of numerical relativity. But they are not in principle impossible. The development of quantum computing may eventually provide the computational resources needed for these calculations, since quantum computers are naturally suited to simulating quantum systems. The connection between quantum gravity, black holes, and quantum information has become one of the most active areas of theoretical physics over the past decade. The discovery that black holes can be thought of as quantum information processors, and that the scrambling of information inside a black hole has connections to quantum error correction and the geometry of entanglement, has led to a deep interplay between quantum information theory and quantum gravity. Ideas from quantum information have been used to prove results about the structure of quantum gravity theories. And conversely, thinking about quantum gravity has led to new results in quantum information theory. The Planck star picture fits naturally into this broader context. If the Planck star is a repository of quantum information, encoding the quantum state of all the matter that ever fell into the black hole, then understanding how it preserves and eventually releases that information is fundamentally a problem in quantum information theory. The entanglement structure of the Planck star and how it is connected to the entanglement structure of the outgoing Hawking radiation is the key question. Answering it requires tools from quantum information theory applied in the context of loop quantum gravity. This interdisciplinary approach, bringing together quantum information theory, quantum gravity, observational cosmology, and theoretical particle physics, represents the frontier of the field. The Planck star is one of the objects that sits at the intersection of all these approaches. It is a black hole interior structure that resolves a singularity problem from general relativity, preserves information in compliance with quantum mechanics, leaves observational signatures that cosmology might detect, and whose theoretical description requires the full machinery of loop quantum gravity. No experiment in the foreseeable future will directly confirm or refute the Planck star, but the accumulation of indirect evidence from gravitational wave observations, gamma-ray surveys, dark matter measurements, and the continuing theoretical development of loop quantum gravity will progressively constrain the possibilities. The space of viable models will narrow, and at some point, whether in decades or centuries, the constraints may become tight enough that only one picture survives. Physics has always been willing to wait for the right observations. The confirmation of general relativity required waiting for a solar eclipse that would allow the deflection of light by the sun to be measured. The detection of gravitational waves required waiting for the development of laser interferometry, sensitive enough to detect displacements of a fraction of the width of a proton. The confirmation of the Higgs boson required waiting for a particle accelerator large enough to reach the necessary energy. In each case, the wait was worth it. The physics revealed was worth the effort. The physics inside a black hole, if the Planck star picture is right, is worth the wait too. It touches the deepest questions about the nature of reality at its most fundamental level. It connects the physics of the larger scales to the physics of the smallest. It resolves, in a concrete and specific way, one of the longest-standing crises in theoretical physics. And it does so not by abandoning the principles of quantum mechanics or general relativity, but by finding the deeper framework that unites them. The Planck star is a prediction from the frontier of human knowledge about the universe. Whether it is confirmed or refuted, the effort to test it will advance our understanding of space, time, matter, and information in ways that cannot be fully anticipated. The history of physics is full of such moments, when a theoretical prediction, however strange it seemed at the time, pointed toward a reality that turned out to be stranger still. The universe at its most extreme does not owe us familiarity. The center of a black hole is not a place where human intuition is a reliable guide. The mathematics of loop quantum gravity, imperfect and incomplete as it currently is, may be pointing towards something real, a tiny ball of energy at the boundary of what spacetime can describe, supported against the ultimate collapse by the granular structure of space itself, carrying within it the quantum memory of everything that ever fell inside. The physics is still being written, the observations are still being planned, the theories are still being developed. But the question, what happens at the center of a black hole, has an answer that is more interesting than anyone expected when the question was first posed. Not nothing, not infinity. Perhaps, if the equations are right, something that looks like the Big Bang in miniature, preserved, frozen, waiting. A Planck star. There is a concept in physics called the correspondence principle. It was articulated by Niels Bohr in the context of early quantum mechanics. It says that any new theory must reproduce the results of the old theory in the domain where the old theory is known to work. Quantum mechanics must reproduce classical mechanics for large systems. Quantum electrodynamics must reproduce classical electrodynamics at low energies and large distances. Any quantum gravity theory must reproduce general relativity wherever general relativity has been verified. The correspondence principle is not just a methodological guideline. It is a consistency requirement. If a proposed quantum gravity theory failed to reproduce general relativity in the appropriate limit, it would be straightforwardly wrong, not just incomplete. This is why the semi-classical limit of loop quantum gravity is such an important theoretical question. The theory must demonstrate that, on scales large compared to the Planck length, it produces the smooth spacetime geometry of Einstein's equations. For the Planck star picture, the correspondence principle operates in a subtle way. The Planck star exists within a black hole, which is itself a region where general relativity holds with extraordinary precision, as confirmed by gravitational wave observations. The interior of the black hole, far from the Planck star and on scales much larger than the Planck length, should be described accurately by classical general relativity. The matter falls inward on geodesics determined by the Schwarzschild or Kerr metric. The spacetime curvature builds according to Einstein's equations. All of this must be reproduced by loop quantum gravity in the relevant limit. Only in the final stages of collapse, when the density reaches the Planck scale, does the discrete quantum structure of LQG assert itself and depart from the classical prediction. This is exactly what the correspondence principle demands. The departure from classical behavior occurs precisely where classical general relativity predicts its own breakdown, at the singularity. The quantum correction replaces the singularity with a bounce. Everywhere else, classical general relativity is reproduced. This internal consistency is one of the attractive features of the Planck star picture. It does not require any departure from well-tested physics, except in the regime where classical physics has already acknowledged its own inadequacy. It is a minimal modification. The quantum effects are switched on by the very conditions under which they must be switched on, Planck scale density, and switched off everywhere else, leaving general relativity intact. Compare this to some of the more radical proposals for modifying black hole physics, such as those involving firewalls. The firewall proposal, put forward in 2012 by Almheri, Marov, Polchinski and Sully, argues that if information is preserved in Hawking radiation through quantum entanglement between early and late radiation, then an infalling observer cannot experience a smooth crossing of the event horizon. The quantum entanglement structure required for information preservation is inconsistent with the smooth spacetime at the horizon that general relativity predicts. Something dramatic must happen at the horizon itself, a firewall of high-energy quanta that destroys any infalling observer. The firewall proposal generated enormous controversy because it seemed to require a departure from classical general relativity, not at the Planck scale singularity, where such departures are expected, but at the event horizon, which for a large black hole is a region of relatively modest spacetime curvature. For a supermassive black hole like M87 star, the tidal forces at the event horizon are negligibly small. General relativity predicts that an infalling observer would notice nothing special as they cross the horizon, at least initially. A firewall at the horizon would violate this prediction in a regime where general relativity is expected to be accurate. The Planck star picture, by contrast, requires no such violation. The event horizon forms normally. The interior spacetime evolves normally according to general relativity on all scales above the Planck length. The departure from classical physics happens only at the Planck star itself, deep inside the horizon, and only when Planck scale density is reached. This is reassuring from the perspective of the correspondence principle. It suggests that the Planck star picture is at least qualitatively consistent with the very successful predictions of general relativity in the accessible regime. The firewall paradox has not been resolved. It remains one of the active puzzles in the field. Some researchers believe the firewall is real, and that the paradox reveals something fundamental about the incompatibility of information preservation and smooth horizons. Others believe the firewall is an artifact of assumptions that will be relaxed in a correct quantum gravity theory. The Planck star picture represents a specific version of the latter view, in which the resolution of the information paradox occurs deep inside the black hole rather than at the horizon. Understanding which view is correct would require either experimental access to the black hole interior, which is impossible, or a sufficiently complete quantum gravity theory that its predictions for the horizon and interior structure are unambiguous. Loop quantum gravity is not yet at that level of completeness, but the current state of the Planck star picture, incomplete as it is, does not obviously violate the smooth horizon condition. An infalling observer in the LQG description would still experience a smooth crossing of the horizon and only encounter the Planck physics when the collapse compresses matter to Planck density. The phenomenology of the event horizon crossing is itself an interesting topic. In classical general relativity, crossing the horizon of a large black hole is a non-event for the infalling observer. The horizon is defined globally as the boundary of the region from which light cannot escape, but locally it is not marked by any special physical condition. The space-time curvature at the horizon of a stellar mass black hole is strong but not extreme. For a supermassive black hole, the horizon tidal forces are negligible. You would not feel yourself crossing the horizon. You would simply notice after the fact that you are now in a region from which escape was impossible. The time it takes from horizon crossing to reaching the Planck density, where Planck star physics begins, depends on the mass of the black hole. For a stellar mass black hole, the proper time from horizon crossing to reaching Planck density for an infalling observer is on the order of microseconds to milliseconds. For the supermassive black hole at the center of the Milky Way, with 4 million solar masses, the corresponding time would be on the order of 20 seconds. For M87 star at 6.5 billion solar masses, the time would be on the order of hours. The larger the black hole, the longer the journey from horizon to Planck density. These timescales are the proper time experienced by the infalling observer. From the perspective of a distant external observer, the infalling observer appears to slow down and freeze asymptotically at the horizon due to gravitational time dilation. The external observer never sees the infalling object actually cross the horizon, but this is an artifact of the extreme time dilation, not a physical barrier. The infalling observer's experience is perfectly real. They cross the horizon and continue falling in their proper time. They simply cannot communicate this to the outside universe. What the infalling observer experiences as they approach the Planck density and the Planck star forms is, in principle, dictated by loop quantum gravity. The geometry of the collapse deviates from the smooth classical trajectory as the density rises toward the Planck scale. Whether the observer would notice anything dramatic, any sensation of the quantum structure of spacetime, any unusual perception of time or geometry is entirely unknown. At such extreme densities, the observer and the surrounding matter would themselves be at or near Planck density. The distinction between the observer and the geometry would become meaningless. The physics would be fully quantum gravitational with no classical approximation available. This is one of the extreme limits of physical reasoning. We cannot directly ask what it would feel like to be in such a situation, because there is no framework adequate to address the question. We can describe the classical trajectory up to the approach to Planck density. We can describe the quantum gravitational bounce in the LQG framework. But the experience of an observer in those conditions is beyond any current theoretical description. It is one of the places where the boundary between physics and philosophy genuinely becomes relevant. The philosophy of physics has grappled with black hole interiors in interesting ways. The question of whether the physics inside a black hole is real, in some meaningful sense, given that it is causally disconnected from all external observers, touches on fundamental questions about the ontology of physics. If no measurement can ever access the interior of a black hole, in what sense does the interior exist as a physical fact? This is not merely abstract philosophizing. It bears directly on the information paradox and on the interpretation of quantum mechanics. The Copenhagen interpretation of quantum mechanics, in its strongest form, holds that a physical quantity has a definite value only when it is measured. Unmeasured quantities are not real. Applied to the black hole interior, this interpretation would suggest that the interior state is not a well-defined physical fact for any external observer. The information paradox would then dissolve, not because information is preserved, but because the notion of information inside a black hole is not physically meaningful. Most physicists working on quantum gravity reject this extreme operationalist view. They take a realist stance in which the quantum state of the black hole interior is physically real, even if inaccessible to direct observation. This is partly because the realist view is more productive for theoretical development, and partly because there is a strong argument that the information paradox has observational consequences through the final stages of Hawking evaporation. If the interior quantum state is not real, it is hard to understand what is producing the Hawking radiation in the first place. The Planck star picture is firmly in the realist camp. It posits a definite quantum state for the collapsed matter inside the black hole, stored in the Planck star. This state evolves unitarily according to the laws of loop quantum gravity. It is real, even if inaccessible. The information it contains is real, and the eventual tunneling to the white hole configuration, which releases this information into the external universe, is a physical process that has real consequences for any observer who waits long enough. Whether this realist picture is correct depends on whether loop quantum gravity is the correct theory of quantum gravity, and whether the Planck star model accurately captures the dynamics of gravitational collapse within that theory. These are open questions, but the picture is internally consistent, physically motivated, and connected to broader frameworks of quantum mechanics and gravity in ways that make it scientifically tractable. The long view of physics suggests that eventually, perhaps not in our lifetimes, the question will be answered. The tools will be developed, the observations will be made. The theory will either be confirmed or refuted and replaced by something better. The history of science is a history of this kind of patient, persistent investigation, pushing the boundary of the known into the unknown, one step at a time. Black holes have been at the center of some of the most productive theoretical and observational developments in physics over the past 50 years. The Hawking radiation discovery transformed them from passive objects in the universe into thermodynamic systems with temperature and entropy. The development of black hole thermodynamics connected gravity, quantum mechanics, and thermodynamics in ways that are still being explored. The application of holography to black holes produced the ADS-CFT correspondence, which has been one of the most fruitful tools in theoretical physics for 3 decades. The gravitational wave detection program opened a new observational window on the universe and confirmed general relativity in a new regime. The Planck star adds another chapter to this story. It connects black holes to loop quantum gravity, to the information paradox, to the dark matter problem, to the nature of the Big Bang, and to the very structure of space-time at the smallest scales. It is a rich and specific proposal that, whatever its ultimate fate, will drive productive research for years to come. If you have followed this exploration of black holes and quantum gravity to this point, you have traveled from the dark stars of the 18th century through the development of general relativity, quantum mechanics, white dwarfs, neutron stars, singularities, Hawking radiation, loop quantum gravity, and the Planck star itself. The journey spans the full breadth of modern physics. The endpoint is not a solved problem, but a sharply posed question, one of the sharpest in all of contemporary science. What happens at the center of a black hole? The answer may be a Planck star, a frozen echo of the Big Bang, a ball of quantum spacetime smaller than an atom, supported against infinite compression by the granular structure of space itself, preserving, within its quantum states, the information about everything that ever fell inside, destined, after timescales longer than the current age of the universe, to tunnel into a white hole and release that information back into the cosmos. Or the answer may be something else entirely, something we have not yet conceived. The frontier of physics is always full of surprises. The discoveries that matter most are usually the ones that no one anticipated. The singularity at the center of a black hole has been a known unknown for half a century. What replaces it is a question whose answer, when it finally comes, will reshape our understanding of space, time, matter, and the fundamental structure of reality. Stay curious. The best questions are always the ones we cannot yet answer. There is another dimension to the Planck star story that deserves attention: the role it plays in our evolving understanding of what we mean by space-time itself. For most of the 20th century, space-time was treated as a smooth, continuous entity, a stage on which the drama of physics played out. Fields existed on it, particles moved through it, gravitational waves rippled across it, but space-time itself was the backdrop, the container, not the content. General relativity changed this partially. In Einstein's theory, space-time is dynamic. It responds to the presence of matter and energy, It curves, stretches, and warps. The stage affects the actors and is affected by them. But in general relativity, space-time is still fundamentally smooth. There is no minimum length. There is no granularity. The metric tensor, which encodes all the geometric information about distances and angles and curvature, is a smooth function that can be evaluated at any point, no matter how small the neighborhood. Loop quantum gravity abandons this smoothness at the Planck scale. In LQG, space-time is not smooth. It is quantized. It is made of discrete, indivisible units. Below the Planck length, the concept of a point in space-time loses meaning. You cannot localize an event to a region smaller than the Planck volume. Space itself has a texture, a graininess, at the most fundamental level. This is a conceptually radical departure from everything that came before. It means that the question of how many points are in a finite region of space does not have a well-defined answer, or at least not an infinite one. The number of degrees of freedom in any finite region of space is finite, determined by its volume in Planck units. For macroscopic regions, this number is still enormous, but it is finite. This finiteness has consequences for physics at the Planck scale, and the Planck star is the most direct consequence for the fate of collapsing matter. The finiteness of spatial degrees of freedom in LQG is also connected to the holographic principle. The holographic principle says that the maximum information content of a region of space is proportional to the area of its boundary, not its volume. This seems counterintuitive. A larger volume should naively hold more information. But if the number of spatial degrees of freedom is bounded by the area, then information is stored at the surface, not the interior. This principle has profound implications for quantum gravity. It suggests that three-dimensional descriptions of spacetime are, in some sense, redundant. The full physics might be encodable in a two-dimensional boundary. The Bekenstein-Hawking entropy of a black hole fits this picture precisely. The entropy of a black hole is proportional to the area of its event horizon, measured in Planck units. For every 4 Planck areas of horizon surface, there is 1 bit of entropy, 1 unit of information. The proportionality is exact. This means that all the information about what is inside the black hole is encoded somehow on its surface. Where exactly it is encoded, how it is encoded, and how it eventually comes out in the Hawking radiation, these are the questions that make the information paradox so compelling. In the Planck star picture, the information is stored in the quantum state of the Planck star itself, but the event horizon entropy tells us that the amount of this information must be proportional to the horizon area. When the horizon is large, there is a large amount of information. When the horizon shrinks to the Planck scale, leaving only the Planck relic, there is only about 1 bit of information remaining. Where did the rest go? In the Planck star picture, it was gradually released in the Hawking radiation over the evaporation time, through the slow quantum correlations established between the Planck star state and the outgoing radiation. This gradual release of information is what produces the Page curve. Don Page showed in 1993 that if black hole evaporation is unitary, the entanglement entropy of the outgoing radiation should first increase and then decrease, turning around at what is called the Page time, when about half of the black hole's mass has been radiated away. Before the Page time, each new bit of Hawking radiation is entangled primarily with the black hole interior rather than with earlier Hawking radiation. After the Page time, each new bit of Hawking radiation is increasingly entangled with earlier bits, and the entanglement entropy of the radiation decreases back towards 0 as the black hole completes its evaporation. Computing. The Page curve from first principles in any specific quantum gravity theory is a major theoretical challenge. Recent progress in string theory, using ideas about replica wormholes and holographic entanglement entropy, has produced calculations consistent with the Page curve. The analogous calculation in loop quantum gravity, using the Planck star framework, has not yet been completed. This is one of the important open problems in the field. Demonstrating that the Planck star mechanism produces the correct Page curve behavior would be significant evidence that it correctly resolves the information paradox. The entropy of the Planck star itself is an interesting quantity. The entropy of a thermodynamic system counts the number of microscopic states consistent with its macroscopic description. For a stellar mass Planck star, the number of quantum states available to the 1 picometer scale object is dictated by the quantum structure of LQG at the densities involved. Calculating this entropy precisely requires knowing the density of states of the quantum spacetime geometry at Planck density. which in turn requires working out the LQG dynamics in that regime. This is not yet done with precision, but rough estimates suggest the entropy of the Planck star should be consistent with the entropy of the black hole that contains it, as required by consistency with the Bekenstein-Hawking formula. The consistency of Planck star entropy with Bekenstein-Hawking entropy is an important check on the picture. If the Planck star had far too few quantum states to account for the black hole entropy, the model would be inconsistent. If it had far too many, the excess information would have no place to go. The rough estimates suggest consistency, but a precise calculation is needed to establish this firmly. Loop quantum gravity's approach to entropy in general is interesting. The first major result in LQG, obtained by Abhay Ashtekar, John Baez, Alejandro Corici, and Kirill Krasnov in 1997, was a calculation of the entropy of a black hole horizon using spin network states puncturing the horizon. The result was proportional to the area as required by the Bekenstein-Hawking formula, with a coefficient that depends on a parameter of the theory called the Immirzi parameter. Fixing the Immirzi parameter so that the coefficient matches the exact Bekenstein-Hawking value is one way of calibrating the theory. This calculation was a significant success for LQG, showing that the framework could reproduce a key prediction of black hole thermodynamics from microscopic quantum gravitational principles. The relationship between the LQG black hole entropy calculation and the Planck star picture is not yet fully worked out. The entropy calculation describes the horizon, while the Planck star is in the interior. Connecting them requires understanding how the quantum states of the horizon are related to the quantum states of the interior, which in turn requires understanding the full quantum geometry of the black hole spacetime in LQG. This is an active area of research. The Planck star also has implications for the thermodynamic interpretation of black holes. In classical thermodynamics, a system in thermal equilibrium has a temperature that describes the average kinetic energy of its constituents. Hawking showed that black holes have a temperature given by the Hawking temperature, which is inversely proportional to the black hole's mass. A stellar mass black hole has a Hawking temperature of about 100 billionth of a degree above absolute zero, far colder than the cosmic microwave background radiation that permeates the universe. Such a black hole absorbs more energy from the CMB than it radiates as Hawking radiation. It effectively grows, not shrinks. In the current cosmological environment, only when the universe expands and cools below the Hawking temperature of a given black hole will that black hole begin to evaporate. For stellar mass black holes, this will happen when the temperature of the CMB falls below about 100 billionth of a degree, which requires the universe to expand by a factor of about 30,000 beyond its current size, a process that will take many hundreds of billions of years. The evaporation timescale thereafter is the 10 to the 67th years mentioned earlier. During the evaporation process, as the black hole loses mass, its temperature rises. The smaller the black hole, the hotter it is. This leads to a runaway evaporation in the final stages. As the mass approaches zero and the temperature approaches the Planck temperature, roughly 10 to the 32 degrees Kelvin, the semi-classical Hawking calculation breaks down and quantum gravity takes over. The Planck star and Planck relic represent the quantum gravitational endpoint of this process. The Planck temperature is the highest temperature at which thermodynamics in the ordinary sense has meaning. Above the Planck temperature, the thermal energy of particles exceeds the Planck energy, the energy equivalent of the Planck mass, and the quantum gravitational effects dominate. In this regime, the concept of temperature in the usual sense may no longer apply. The physics is fully quantum gravitational. The Planck star, at the endpoint of evaporation, exists in this realm. What does it mean for the Planck star to have a temperature? In LQG, the quantum states of the Planck star can in principle be enumerated, and a statistical mechanical temperature can be assigned based on the density of states. But the relationship between the statistical temperature and the geometric temperature of the surrounding spacetime is not straightforward. The usual tools of quantum field theory in curved spacetime, which are used to derive the Hawking temperature, apply when the spacetime curvature is small compared to the Planck scale. Inside the Planck star, the curvature is at the Planck scale. Different tools are needed. Developing these tools is one of the challenges of loop quantum cosmology and loop quantum gravity as applied to the Planck star. The team around Rovelli and Vidotto, along with collaborators around the world working in the LQG framework, are actively developing the methods needed to address these questions. The field is young and productive. The techniques being developed for the Planck star will also be useful for understanding the big bounce in loop quantum cosmology and vice versa. The cross-fertilization between the two applications of LQG is one of the strengths of the approach. Ultimately, the Planck star story is a story about the remarkable coherence of nature at its most extreme. Every time physics has pushed to a new scale, a new regime, a new extreme of energy or density or curvature, it has found that the laws do not simply break, they transform. Quantum mechanics is not the negation of classical mechanics. It is its generalization. General relativity is not the negation of Newtonian gravity. It is its generalization to high velocities and strong fields. Whatever quantum gravity theory eventually emerges and is confirmed, it will not negate general relativity or quantum mechanics. It will be their generalization to the Planck scale. The Planck star is a glimpse of what that generalization might look like. Not a singularity, but a bounce. Not a point, but an extended quantum object. Not a dead end, but a transformation. Not the end of the story for the matter that falls in, but the beginning of a new phase. Frozen in time from the outside, dynamic from the inside, eventually returning to the universe the information it temporarily held. Whether this is the final answer or a stepping stone to something even stranger, we cannot yet know. Physics at this frontier is always a work in progress. The equations will be refined, the approximations improved, the observational signatures sharpened. The theory will make contact with observation at some point, however indirect. And the question that has animated a century of work in gravitational physics, what happens at the center of a black hole, will eventually have a definitive, experimentally supported answer. For now, the Planck star is the best answer available from the framework of loop quantum gravity. It is compelling, coherent, and consequential. It replaces infinity with something finite. It replaces destruction of information with preservation. It replaces an ending with a transformation. And it does so by taking seriously the one physical principle that no other attempt to resolve the singularity had fully respected. That space itself, at the smallest scales, is not a smooth continuum, but a granular, quantized fabric, and that the structure of that fabric is the last defense against the ultimate gravitational catastrophe. The name Planck star honors Max Planck, the German physicist who in 1900 made the first step toward quantum mechanics by proposing that energy is exchanged in discrete packets. Planck's insight came from a practical problem, explaining the spectrum of radiation emitted by a hot object, and it set in motion the revolution that produced quantum mechanics, quantum field theory, and the standard model of particle physics. Planck himself was famously conservative about the radical implications of his discovery. He expected that the discontinuity of energy exchange was a mathematical tool that would eventually be explained away by some deeper classical mechanism. Instead, it turned out to be a fundamental feature of nature, the Planck length, Planck time, Planck mass, and Planck temperature that bear his name were first identified by Planck himself in 1899 as the natural units of physics that emerge from combining the fundamental constants of nature, the speed of light, the gravitational constant, and Planck's constant. He noted that these combinations produced length, time, and mass scales that were independent of any particular system of units, universal to nature itself. He did not know what they meant physically. He recognized them as mathematical curiosities. A century later, they are recognized as the scales at which quantum mechanics and gravity must both be simultaneously important. The Planck length is not just a characteristic scale. In loop quantum gravity, it is the minimum size of a spatial quantum. The Planck mass is approximately 22 micrograms, the mass of a grain of sand. But concentrated in a Planck length volume, it corresponds to Planck density, the density at which quantum gravity effects dominate. The Planck time, approximately 5 × 10⁻⁴ seconds, is the shortest interval of time that has physical meaning in the quantized spacetime of LQG. The Planck star operates at these limits. It is where the discrete, granular nature of spacetime asserts itself against the crushing force of gravitational collapse. It is the physical realization of the scales that Planck identified as fundamental, now playing a direct and decisive role in the dynamics of a collapsing star. There is something fitting about this connection. Planck's discovery of the quantum was motivated by the behavior of radiation at high temperatures. The problem he was solving involved the ultraviolet catastrophe, the failure of classical physics to predict the spectrum of a black body at high frequencies. The quantum resolved this by preventing the infinite accumulation of energy in high-frequency modes. The Planck star resolves an analogous catastrophe in gravity, the ultraviolet catastrophe of infinite density, by preventing the infinite compression of matter into a point. In both cases, the quantum introduces a natural cutoff that prevents an infinite from becoming physical. The deep connection between the two problems, Planck's original radiation problem and the Planck star's gravity problem, runs through the fundamental constants that define the Planck scale. The Planck star is, in this sense, the completion of the program that Planck began. The quantum tames the ultraviolet, in radiation and in gravity alike. Whether nature has implemented this solution through loop quantum gravity specifically, or through some other theoretical framework, remains to be determined. The Planck star is a prediction of LQG, not an observation. But it is a prediction that is physically motivated, mathematically grounded, and connected to real theoretical and observational programs. It is the kind of prediction that drives physics forward, not by providing an answer that closes the question, but by sharpening the question, identifying what we need to measure or calculate to distinguish between possibilities. The search for that measurement or calculation continues. The Planck star waits, if it is real, inside every black hole, frozen, quantum, infinitely patient, a grain of spacetime holding the memory of a star.